Good morning, everyone. Okay, we're going to go ahead and get started. I have to say it's a real pleasure to see this room full of all of you. It's been a long time getting to this point, and it's great to see you here, so thanks for coming. Also, thanks to all of you who are joining us by webinar. We know that there are dozens of you who are registered to do that. Thanks for joining us in virtually and being part of the discussions. Please participate in Q&A. Like I mentioned, we will be alternating questions in sessions. We've got somebody monitoring the webinar Q&A in every session, so we'll try to integrate everybody as much as we can in that. It's been a great pleasure to work with the other members of the local organizing committee and Shane and the scientific organizing committee, our conferences and visitor services staff, and the AV staff here in the Stamp Union. We didn't expect all of the challenges that we've had in the last couple of days. The fact that we had the power outage to recover from, all of the preparation that we were planning to do yesterday, we've done in the last hour and a half, basically, in terms of getting set up with the testing, the getting settled into the room and figuring out the details. But we think it's all working now. We think we are live for the people online, and happy to have you here. I do have a couple of logistical notes. One is that the welcome reception will in fact be tonight, rescheduled from yesterday. So when the sessions end at 5:30 today from the parallel sessions, just go ahead and head back upstairs to the Colony Ballroom, and we'll have some light food. We'll have a cash bar. I will need a drink, I'm sure, by then. So we hope that'll be a nice time. So that'll be from 5:30 to 7. For the posters, due to a combination of factors, we're not ready to put up the poster boards and the posters today. So looks like we're going to get the poster boards tonight after the reception ends. So if you brought your posters today, I apologize that you won't be able to put it up today, but you'll be able to put it up tomorrow, and then we'll have those up for the rest of the week. And we're looking forward to a very lively session on Thursday to be in live. But also throughout the week, please take a look through the posters and store mental comments of which ones you want to ask the presenters about. Last thing I want to say is that one of the things that's great for me, and I think for a lot of you, is that this brings together a wide cross-section of people, some very experienced, some getting new to LISA science or technology, some just trying it out and seeing what this field and the community is like. And so this is a great opportunity to meet people, as well to talk with your old friends whom you maybe haven't seen in person for a while. In the sessions, with the discussions, and in between, we hope you have a wonderful time here and a very productive week. With that, I'll turn it over to Shane Larson as the chair of the Scientific Organizing Committee, and we'll get started. I'll just say one more time, we're still figuring things out, so if there's a pause or a glitch or something, we'll try to get it solved as quickly as possible. Thanks for your patience. All right.
Okay, thank you, everyone. I am, just a sec, I'm following my instructions here to make sure everything's muted. It looks like they are. Thank you, everyone, for being here. My name's Shane Larson. I'm from Clarkson University in New York. I am the chair of the Scientific Organizing Committee, this LISA Symposium. It's great to be here at the University of Maryland. I was looking back through my notes. The very first LISA Symposium I ever went to was LISA 4, which was at Goddard, just down the road here, so it's good to be back in the area. It's great to see everyone here, so thank you for coming. Thank you for all the work you put in, my local organizing committee, our scientific organizing committee. It's been a long voyage, and we're glad to finally be here. I just want to take a few minutes to thank all of you who are here. We have over 350 total participants, and so there is a massive amount of LISA science that we as the Scientific Organizing Committee had to look over and organize. We did our reviews for the scientific program blindly. That means we took all of your names and institutions off your abstracts, and then we went through as a way of ensuring that we just looked at science and decided what we thought would be useful to have in the scientific sessions. Some of you will know notice in your sessions that the sessions are a little more mixed than in the past. Some of them are very pure. They'll look like you're just talking to the people you're used to talking to. But as we get closer and closer to LISA, the time for all of us to be interacting and understanding what each other does becomes more critical. And so we've made some effort to mix scientific sessions up. So there will be data analysis mixed with multi-messenger astronomy, mixed with astrophysics, mixed with noise assessment, all kinds of different things. So in some of your scientific sessions, you will see talks and people that are maybe not the ones you're used to seeing, but hopefully will provide some moments for inspiration, some crosstalk, and kind of moments to do new and different things. Okay? So we are about 10 years from LISA. 10 years from now, the LISA Symposium in 2036, we should be a year on our way to cruise. And so that will be a very different LISA Symposium than it is now. But this is special to be in the room together when we're getting ready to really start moving forward in a way that we've been thinking about for a long, long time. Those of you who are young, you're just beginning in LISA, so you'll see what this looks like for your whole career. You'll never be in a career without LISA. Some of us have slowly grown into this, and so it's exciting to see it finally happening, and we hope we're here at the LISA Symposium in 10 years when we're finally on our way. So with that, I am going to start by introducing Shawn Domagal-Goldman, who is the Astrophysics Division Director at NASA. We're very fortunate to have him here with us this morning, and so he'll say a few remarks before we start our first session.
Good morning, everybody. Welcome to the 2026 International LISA Science Symposium. Before we get started, you know, when you plan a wedding, plan for something to go wrong, they don't mean the power going out the day before your conference starts. So could we just give a shout out to all the tech crew in the back that scrambled this morning, get us online, and for Peter, Shawn, and Shane, and the organizing committees for getting us all here today. Thank you all. Again, I'm Shawn Domagal-Goldman. I am the Division Director of Astrophysics at NASA. That means LISA is one of the many things that I have the privilege of leading on behalf of the agency across our astrophysics portfolio. And across that portfolio, there's no place I'd rather be than right here, right now. This is a meeting that all of you have been, well, some portion of you have been coming to for the last 30 years. I know we have some first-time attendees like myself here as well. But the work that's done here this week and in prior weeks like this is absolutely critical. It's absolutely critical. This is a group of people, a community that have come together across borders, across time zones, across agencies with a vision for an incredibly precise observatory that won't just see but will sense the very fabric of the universe, that will probe that fabric and will extend our sensory horizons out to the very edge of the universe. I can't think of anything cooler than that. And that's possible thanks to the people in this room coming together to make it happen. And that starts with the science. That starts with the science. The ideas that are going to be shared here this week are what are foundational to our partnerships. And I don't have a more important partnership than this one. This is the single most important critical partnership to my portfolio across the entire astrophysics fleet at NASA. And so when I say I'm thankful to the scientists, the community members, the project managers, the leaders in this room, I am truly sincere. Because without the science collaboration across borders that's represented here, this wouldn't be a part of the astrophysics portfolio. And I'm happy to report great progress that we've made in the last year and a half. I'm thankful, first of all, for very patient leadership from our partners at ESA. I'm thankful for the partnership with ESA to start, but I'm thankful for their leadership at this partnership. Because it's been a very, very difficult year and a half, lots of uncertainty, a lot of the first time this has ever happened. And it's taken that patient leadership to steer us through. And so I want to thank our partners from ESA for getting us to where we are today. And on the US side, despite that uncertainty, despite that, well, this has never happened before many Fridays, The project here in the US has continued to make steady progress. And I want to give a shout out to Julie Lander, our project manager on the US side, for making that happen. And that's important, right? It's important we thank each other because we are, like these projects, the 30 years, right? You all have been coming together for 30 years. I hope you're going to come together for another 30 to see us through the rest of this project getting to launch and then to see the science returns that I mentioned before. I want to close with a couple more comments. I think you're probably picking up the vibes on this, but this is an important partnership to me. I've talked to my boss, Dr. Nicola Fox, who is the Associate Administrator for Science at NASA for all of science across our 5 divisions. And this is one of her top priorities as well. And so I'm meeting with Administrator Jared Isaacman on Wednesday morning with some of the project leadership from the US side to make sure that he understands how important this mission is for the United States of America and for NASA. One more thing I want to call out, because I see a couple of our partners in the room. I want to shout out our US partners from the industry side because they've made great progress, and it's part of the reason we are through KDP-B. So shout out to KDP-B getting passed on the US side. This is the first official gate that we've passed in the last 30 years of this mission, and it really helps us build some momentum into this year, and I look forward to a successful KDP-C next year. For those that are first-timers or new to this endeavor, those are the sort of NASA gates. KDP is key decision point. It's like we pass a certain threshold for the mission to get it to its next stage of advancement. So that's all I really have to say, other than to say enjoy the week. For those traveling, thank you for coming. I look forward to your Instagram posts about ranch dressing and oversized American food portions. Good luck to your respective teams in the World Cup, although I have deep, deep faith in my own US men's national team. And enjoy the science. I said it before, I'll say it again. These partnerships are critical. The science behind the missions is not just what drives them forward, but is what is foundational to the partnerships themselves. And there's no partnership more important to me than this one. So please enjoy the week, enjoy the ranch dressing, and enjoy the science. And thank you for your time.
Okay, everyone. Well, thank you, Shawn. Thank you, Peter, everyone. It's time to start what we came for, which is our first plenary session. We will have 30-minute plenary talks, 25-minute plenary talks with 5 minutes for questions and afterwards. We do have a large fraction of our community online who are participating virtually, so when we do get to the Q&A, we have mic runners who will run microphones around to people in the room. So if you do have a question, please wait for the microphone to arrive at your location. Additionally, I will look to our webinar folks if we have questions online, so we will pause to take questions from our online community as well. Okay? So without further ado, we'll introduce our first talk is Nora Lützgendorf from ESA. Nora's going to give us our LISA mission overview and status talk.
Do I start it here? Or?
Yeah, this one. You should be able to push play. There you go. Okay, and this is your remote.
Okay, thank you, Shawn. Shane, sorry, and Shawn. Too close of a name. Yes, I'm super happy to be here, super excited for this symposium, and also really excited to kick us off with the LISA overview talk. So you will hear 3 talks from the ESA side on LISA. I will give an overview because I think we have, is that working? Yeah. Okay. I think we have a couple of new people joining us, right? You're just joining the consortium maybe, or just this conference, and you haven't really, you know what LISA is, but you haven't really heard everything about it. So I will give an overview, which will not be anything new for our veterans. But the second half of the talk, I will also talk about our project update, where we are right now, what kind of developments we had in the project, and that will be on behalf of our project manager, Filippo, who couldn't make it today. So before I start, let's see if this works. Whoop. No, maybe I do this. Yeah. Okay, before I start, I wanted to give maybe this is this thing. Maybe. I wanted to do a little advertisement of our research fellowship that we have at ESA. So if you are in this kind of career stage, so you're a PhD student and you're finishing up and you want to do a postdoc, or you have a student in this career stage, this is a really cool fellowship that is for, unfortunately, only nationals of ESA member states, so for the European side. But it is an independent fellowship that you can do your research with if you want to be closer to the ESA missions, and especially if you want to be close to LISA. You can do this in 3 different sites of ESA, in the Netherlands, in Spain, and even at STSCI, and can do your independent research or for up to 20% functional work. It's really cool. I can recommend it. I did this fellowship myself. And we will come out with the position pretty soon this summer, but if you want to stay up to date with all of those kind of positions coming out at ESA, sign up to our newsletter, and then you get all of the news that you need from ESA. Let's see. No, this is this guy. Okay, I'm going to go with this. Second little ad, before I start my talk, I promise. You will hear a ton of acronyms during this conference, especially in the more technical talks, right? And this is just how the way it is with LISA. We have a lot of acronyms. I've created an acronym dictionary that you can either download as a Python GUI, or you use the web interface, or even make your little app on the phone so you can type in the acronyms during the talks and get like a good translation, hopefully. And you can help me to make this better. If you find acronyms that are not in the dictionary, send me a message or put it on the Git in a ticket or so on, so that we can grow this dictionary to make it more accessible for everyone. Okay, let's start with the actual talk. So I like to start all my talks with videos because they're nice and pretty and give us a warm, fuzzy feeling of seeing pretty colors. 2 years ago, at the LISA Symposium in Dublin, I gave this talk as well, and I showed a video from the LIGO collaboration. And it was a is that not working?
We're just trying to not obscure your slides.
Okay, it's all good. Yeah, videos. And I said, hey, look, guys, I really want to have videos like this for LISA sources, right? Not just LIGO sources. Somebody snarky was telling me just to change the timescales for the merging black holes, which is true, you can do that. But showing, unfortunately, being a bit choppy here, showing actually Emery's videos was something that I really wanted to do. So now we actually have a code that makes those pretty videos, and you can just put in waveforms and trajectories, and you make those videos. So if you're interested in that, to make your own videos, let me know. I'm going to make this code public eventually, but I also happy to give you code or videos anytime for like nice public talks. Okay, now let's see if this is, okay, good. Still some technical difficulties. Okay, let's talk about LISA. And I like to always start with a little history on LISA, right? Because we need to remember that this is it's a quite old idea, and it goes way back before even I was born. And probably many of you guys were born in the 70s already. I think we always need to acknowledge that the first idea from LISA came from Pete Bender, who was thinking about doing space-based gravitational wave detectors in the 70s already. Unfortunately, we lost Bill and Pete. Oh my God, my name was totally off today. We lost Pete in 2024, right after the adoption of LISA, but he is pretty much considered the forefather of LISA, the idea of doing this in space. And then there were some really cool ideas in the 80s by NASA. So this is a NASA concept document that we found, which really was exploring all different ways of doing gravitational waves in space. And I wanted to show you some because I thought they were really cool. The first one is the Doppler and ranging transponder, DART. So that was trying to measure gravitational waves from really Doppler radial velocities. That was a concept that would have only caught really the brightest events, like the very high signal-to-noise ones, so the sensitivity wasn't great. But it was a cool idea, and the idea started with one spacecraft and then 2 more in the Lagrange points to increase the sensitivity. The next one, is one of my favorite, was the Laser Interferometer Gravitational Wave Mission, which was supposed to be this big structure in space, like a real rigid structure of this cross of 1 kilometer, and then the beam basically going back and forth through mirrors with holes to make the efficient arm length longer. Really cool concept, and also imagine we would have this structure now in space. We could probably see it. Would be great. And you see this this illustration where they built the structure with the space shuttle. Really cool idea. And then the third one in this document, in the 80s, remember, in the 80s, we have something that looks very much like LISA already. And that was called the Laser Heterodyne, cannot pronounce this, Gravitational Wave Mission. And it had 3 spacecraft. They were millions of kilometers apart. They were in heliocentric orbits. We're using laser interferometry with a heterodyne technique, right? So very close to what we have today on LISA. Then we come to the 90s, and that was when LISA was first proposed for ESA, for an ESA mission, and this time as an M-class mission. And so ESA has different sizes of missions, small, medium, large, right? And that depends how much they cost and how ambitious they are. So back then it was proposed and was already called LISA as an M mission. It was unfortunately quite ambitious for an M mission because it had 4 spacecraft, so it basically was a microsynth interferometer in space. So this didn't go much further, but it was the first idea really of that concept there was born. And then we had a couple of ups and downs, right? LISA, everybody was excited, but imagine this were the 90s. So people didn't even measure gravitational waves on the ground yet by this time. So putting something in space for so much money without even knowing that you can actually measure gravitational waves was extremely challenging or extremely ambitious. But then we come to the positive milestones in 2015 when we had the successful launch of LISA Pathfinder. And LISA Pathfinder is our technology demonstration mission, so we usually used just 1 spacecraft and tried to demonstrate that we can have those test masses flying in this very, very stable and calm environment that makes it possible to measure gravitational waves. And that mission was extremely successful. We performed better than we thought. And then remember, in 2016 was also the publication of the gravitational wave detection on the ground with LIGO. So this gave the whole thing a whole new wind and uplift to then come to the successful proposal of LISA in 2017, this time as an L-class mission. And at ESA, the L-class missions are our biggest missions. They stand for L for large, but also for leadership. So those are missions, those are our flagship missions, right? Those are the missions that our Director General usually shows everyone because this is so cool and so great and something new. So we have a completely new status at ESA now as really one of our flagships. So after 2017, we had a very nice study phase, smooth sailing, really studying what we can do there. And then we had, in 2024, the adoption, where we then moved from a study phase to the actual project phase and the implementation phase of LISA. So that's where we are right now. I'm not going to talk about science today. This is just a reminder what our science topics are, right? We do everything from astrophysics over cosmology and even particle physics. If you're new to LISA and you want to read more about our science topics and about the mission itself, I put in the link for the Red Book. So this is our document that we wrote at adoption, where you can read everything about it. It's a very nice and still pretty up-to-date document. So again, I'm going over this quickly. This is just the mission concept of LISA, right? What we're doing, measuring gravitational waves. They change distances in space. So we have 3 spacecraft in a triangular constellation of 2.5 million kilometers arm length, and we are measuring the distances between our test masses with laser interferometry. The trick is we need to measure distances of the order of 10 to the minus 12, so picometer distances. Accuracy. Here are the orbits. Again, probably nothing new for anyone. What is cool about those orbits is that those are all heliocentric orbits. Our spacecraft are in free fall around the sun, and if you see in a second, you see the orbits being blended in. So it is not really us keeping the triangle, they are forcing them as a triangle, but having this beauty of orbital mechanics keeping this triangle in place if you do the right orbit insertion and the right inclination. This is just to show you the main components of LISA, and we will hear more about them in detail throughout this conference, of course. So we start with the gravitational reference system, and now we're starting with our acronyms, right? I'm trying to always translate them, but we are getting in the more technical part, so there will be acronyms. So the GRS, those are our test masses, and that are sitting in our vacuum chamber. And in this vacuum chamber, we have them sitting in our electrode housing. So we have electrodes on the side that help us sense where the test mass is going and can actually also push the test mass with electrostatic fields. So this is something we tested with LISA Pathfinder very extensively. And you will hear a talk, I think, later today from Rita about the GRS in total. Then we go to our optical bench and the interferometers, right? They also sit right there that we need to measure the distances. And we have several interferometers, and I think you will see a talk by Ryan later, like tomorrow, on this whole system as well, so I'm not going into more details. The lasers, they're provided by NASA, so those are Nd:YAG ring oscillators with 1064 nanometers wavelength and about 2 watt, We have 2 of them on each telescope, on each spacecraft. And then the telescopes, they are super nice. They are one of my favorite parts. And they're made out of cerudur. This is a type of glass. And if you get the chance, I'm not sure if there will be a tour to Goddard, and you get to see them. It's really nice to see a glass telescope. Oh, Anne is nodding, I hope. So it's really nice to see it because you can see the light shining through it. And yeah, you don't see a glass telescope every day. So take the chance if you can. And yeah, we will have a talk about the optical metrology system. So that's the lasers, the telescope, and the interferometers also in this conference. It's just a little video, and I hope this time videos work, of the spacecraft. The talk after mine will be talking all about the spacecraft, so I'm not going to give anything away. It's just like we have our final design now, and you see how it looks from the inside with the lasers coming out those tubes. It's not really big, it's 4 times 2 meters about, and we will stack them on top of each other for launch. So this slide became a little bit more convoluted because we had more and more people contributing to LISA. I have tried to update it with the contributions also to the DDPC, the Distributed Data Processing Center. Please don't kill me if I forgot anyone. I hope I put everyone in from the member states. So it's a big effort between ESA, NASA, and our member states, right? The member states also produce hardware and they contribute to the data processing. For the DDPC, we even have non-member states participating, such as New Zealand and Singapore and Canada. So it's really exciting. Everybody wants to be part of LISA. And yes, so you can see also who's responsible for the subsystems, and you can see the contributions of NASA, which are the lasers, the telescopes, and the charge management device, as well as the NASA Science Ground segment. Here's just a organization of our ground segment. Just a quick overview how we do the data analysis, right? We start with like the L0 to L1, so the initial noise reduction is done by ESA, and then we give this to our 2 pillars of the science ground segment, which is the DDPC, the Distributed Data Processing Center, and which is run by CNES, and the NASA Science Ground segment. They do the global fit, and then we bring this back together and trying to make the catalog out of those L2 data sets from them. And this has been done with the LISA Science team. So speaking of the LISA Science team, this is our current composition, right? We have a few people here today during this conference, so please go and talk to them. They're all extremely nice. They are your representatives as for the community to ESA. So if you have any concerns, please bring it up to them. And I don't want to talk more about the science team because we will actually have a talk on Tuesday by Valeria, one of our science team members, and she will tell you what the science team was up to in the last couple of years and what we have produced. Good. Now that we have done the mission overview, and I'm sorry, I went to this quite fast, we're going to talk a little bit about the mission status. But before I start, I wanted to give you a quick run-through what we do actually at ESA in terms of reviews, because we always talk about all those reviews that we're doing. We do the CDR, the PDR, the SRR, and it's not always clear what that actually means. So I try to make this a bit more clear in this diagram, that for each big project at ESA, for each mission, we have a certain set of reviews that we do for all of our mission parts. And with mission parts, I mean the payload, the mission, and the ground segment. And we do this at different times, because the payload needs to be ready first, then the mission needs to be evaluated as a whole, and then the ground segment comes last because it has to be ready last. So we start with the Systems Requirements Review, or SRR, and that is really at the very beginning when we write our requirements. We look, are they all complete? Are they flown down properly? Are they realistic? Are they doable? This is the first review, and for many of our payload things, we already have done this. Then we come, and between those reviews, so between the SRR now and then the preliminary design review, we start designing the whole thing. At the preliminary design review, we start looking at, is our design mature? Is it consistent? And does it actually meet the requirements? So do we have a good plan on what to do? And once we pass this review, we go into actually building prototypes. And these are also called models, right? We have engineering models and things like that. But Juan, Pablo will tell you more about those models. And once we have done this and we have tested those things, we go to the critical design review. And this is now looking at, is the design finished? Is it ready to build and actually to fly, right? So after the critical design review, this is a critical review, as the name says, we will actually start building flight hardware. And the last review before flight is the flight acceptance review, where we check, are we ready to fly? So this was just a little crash course because I'm going to mention SRR, PDR in the next slides a little bit more. So where are we currently at with our progress? So we have on the spacecraft side, and you will hear more from that from Juan, we have our industrial consortium almost built up. So if you don't know how this works, we actually gave our contract to OHB, our main prime contractor, to build the spacecraft, and then OHB is outsourcing all the different parts to European companies to build like specific parts, and that's called the Industrial Consortium. And we're almost complete with this and almost have all our contracts set in place. So that is really a great progress on the spacecraft side. Then the payload, we have a lot of preliminary design reviews going on. We had the gravitational reference system just closed out in April. We also had the interferometric detection system, PDR, I think around now. I'm not sure exactly where we are, but that was planned. It was a delta review because we didn't quite finish this last year. And we have a big restructuring going on in this field, so we're actually getting rid of the term IDS, and I'm going to talk about this a little bit more in the next slide. And then there was some development with the optical bench. So we had some responsibility transfer from the optical bench because there were some funding issues from the UK side, and ESA has taken over the funding. But we keep the expertise in the UK right now, so to not really let the schedule slip. And so that didn't really affect our schedule. It was really just a transfer on who is actually now responsible for it. And we have currently a lot of PDRs, preliminary design reviews, going on for the hosted units on the optical bench, so what's sitting on the optical bench. On the ESA side, we have mission PDR coming up. So again, this is now for the full mission, the preliminary design review. Is our design ready to actually start building more prototypes? And we have started really doing our analysis loop, so really looking if our design is up to date and what we can improve to prepare for PDR, and our kickoff is end of this year. So this is a big milestone, and it will close out next year. For the ground segment, we're gearing up for our systems requirements review, or just ground segments requirements review. So again, this is the earlier review where we look at our requirements for the ground segment and make sure that they are all complete. And this is planned for early next year. And then we have a new baseline for our optical assembly tracking mechanism, and I will talk about this in the next slide, because this is a nice example to show you how this project term actually works, right? We get more mature in our designs, and sometimes we encounter problems that violate our requirements, and then we need to come up with solutions. And here's a good example. So the optical assembly tracking mechanism, or OIATM, is the system that helps us to account for the breathing angle of LISA. We are not always a perfect triangle, right? Our angle will breathe. It's not always 60 degrees. It's 1.5 plus minus degrees. And that system was basically tracking this breathing angle. The problem with this system is that it was giving us quite some noise, especially in the low frequency, and it would affect also our waveform sensing. So we realized we are not really conform with our requirements there with the system working as it is. So we went to a new baseline, and we decided we keep one of the motors stable and just moving the other one, and then using spacecraft rotation for much bigger angle movements. And that is actually quite a nice solution because it makes things simpler, and it actually keeps us within the requirements in terms of the noise sources. So this will be our new baseline on this. We still have to do some testing, but it looks very promising, and it looks very possible to do that. So again, very good example of like, we are encountering problems, we change our design slightly to make things conform again with our requirements. Then we have some developments, as I mentioned earlier, with the restructuring of the interferometric detection system, the IDS. Right? In the past, we had that system, which was basically the optical bench and its hosted units and the phase meter, but it didn't really quite make sense to call this the interferometric detection system without also including the telescopes and the lasers, because they belong to this. So we changed this to the optical metrology system as the overarching thing. And then the optical metrology system consists now of what used to be the IDS, the telescopes, and the lasers. And we split up the IDS, so we got rid of the name IDS, basically, in two different parts. And now we're coming into more crazy acronym regimes. It was not my idea to call it like this, but it was the Signal Detection Processing Chain, the SDPC, and the Optomechanical Chain, the OMC. So the system, the signal chain is basically the brain and the detection and processing of the signal, so the phase meter, the quadrant photoreceivers, the interferometric processing unit, so everything to read out the data. And the optomechanical chain is like the optical, like light path. It's the optical bench and its hosted units. So this is how we split this up. And you can see we split up the responsibilities, with ESA taking more responsibilities on some of those subparts. Again, this is probably too much information, too much in detail, but in case you come across those acronyms, that you know what that actually means. And then I wanted to mention something that is probably going to be the elephant in the room, and people will ask about it, so I wanted to be upfront what we're doing. It's not a secret, right? It has been published. It's our NASA mitigation activities, because unfortunately, as you know, there were some uncertainties on the funding on NASA's side. Last year with the presidential budget request, and this year looks much better because we have a line item, but it's still a risk, right? And if it's a risk in a project, if the risk becomes quite probable and quite severe, because without the NASA contributions we couldn't fly, then project management has to take action to do something. They need to do a mitigation strategy. And that is what we've been doing in the last year. We have started to outsource contracts for those contributions to European vendors. And those are phased contracts, so we gave them a phase 0 contract, so a study contract to study what's feasible and what they can do and to create like the first little models on this. This will go till the end of the year, and then we will see and reassess the situation. This doesn't mean that we will replace those things with European contributions. It is really just to cover our bases, to not lose our schedule in case, in the unlikely case that NASA will drop out. So this is really just something that I think created a lot of fear and rumors, but it's a normal thing that we do in projects to really make sure we are staying on time. So currently we are processing on this, progressing on those elements on different phases, and we would be able to hit our 2035 deadline still if we would have to fall back on those solutions. Okay, just a reminder, those are our reviews, and because I'm showing you now the kind of timeline for this year, you can see we have a ton of preliminary design reviews going on the payload, right? We closed out on the science diagnostic system earlier this year, and we have your hosted units of the optical bench, so the BAM and the PAM, so the beam alignment mechanism and the pointer angle mechanism coming up this year. And then we have all those preliminary design reviews on the GRS hosted units, so all the subunits of the gravitational reference system coming up as well. And then you see down here the interface verification model is actually currently built, which is really cool. So this is a model of the LISA core assembly. So really the basic core of our instrument. This is the two MOSAs and the structure with the telescopes. And that is being built so that we can test for mechanical loads and for the interfaces. So this is really a prototype for us to prepare for the preliminary design review, which we will kick off end of this year. And then you see the ground segment. Again, there's not as much reviews going on right now. We have progress meetings twice a year, which are really good, where the project comes together with the ground segment, with the MOC, and with NASA and with the DDPC, and we talk about how we're going to do this. And these are really, really interesting meetings and very productive meetings. So we think have the DDPC gearing up also with their requirements review to prepare for the requirements review of the ground segment next year. This is how it looks until launch. So this is a little bit more like course schedule. You see our PDRs of the payload, followed then by all the CDRs of the payload, so the critical design reviews. And then you see very nicely how it's staggered for the mission and for the ground segment until we all reach this one final review, which is the flight acceptance review 1 year before launch. And I think this is my last slide. This is just a different representation of how the timeline looks like, just for you to remember where we currently are, somewhere here in the middle of our payload PDRs, and with the different timeline mission reviews that are coming up in the, I think only in the 30s we are really starting to build hardware for the spacecraft to fly, which is quite a timeline. But it's coming up soon. We are still absolutely on time, which is great, and still absolutely planning for launch in 2035. And with this, I am done, and thank you very much.
Okay, thank you, Nora. That's great. So those of you who are wearing the conference t-shirt, you'll see the same design there. I will note that Nora, in addition to being our scientist, is also the artist who created this symbol here. So, Nora is the t-shirt artist. Do we have questions from the room? Please wait for a mic if you do. I will ask one to start with, Nora. So, you know, I'm a theorist, I'm not an instrument person, so I see all these schedules and everything. And so the question that I actually get asked a lot, but I also wonder is, when we look at that big long schedule and all of these reviews, when's the moment they're gonna start making hardware that's actually gonna go to space?
So that depends on payload and spacecraft, right? For payload, we're actually gonna start already in this yellow phase, so end of 28, 9, so before the 30s, we will actually build payload flight hardware. And for the spacecraft, it will happen after the critical design review, so in 2030s.
So the hardware that's being built now is just testing in anticipation of that?
Those are models, prototypes to test things.
Okay,
yeah.
awesome. Other questions from the audience? Any from our Zoom webinar? Bravo.
Yeah, I mean, hoping there's no questions, so good.
Okay, great. Well, let's thank Nora one more time. Thank you, Nora. So our next speaker, yes. Oh, one question. Here.
Okay, we had a question just come in. Concerning the MOSA OATM, how is redundancy done?
Okay, yes, because we now only have one. I think this is still being discussed, how to do redundancy. You don't always have to do redundancy by building two things, right? You just need to make sure that this one thing works in different ways. I have not the exact details how we do redundancy, but it's been talked about, and it's definitely planned to make sure that it's working in a redundant way.
Okay, we good? Everyone? Okay, are you ready, Juan? Okay, our next plenary is Juan Pablo Rodriguez García. He's going to talk to us about the LISA spacecraft, and Peter's running to get the talk online.
Well, LISA is always presented as a scientific mission. I disagree, at least for the next 30 minutes. Because when we talk about LISA, we always talk about the scientific aspect of this mission, but today I would like to focus on something completely different. So, okay, as I was saying, I will focus today on something completely different, the engineering that makes LISA possible. Because, well, we will hear these days a lot about the science behind LISA, but this is thanks to a combination of engineering challenges. And today I would like to put the science aside and take you behind the mission and show you the engineering that will make this mission possible. So you may have probably seen already this picture. So LISA is a constellation of 3 satellites in a triangle shape, separated by 2.5 million kilometers, measuring variations of distances less than 10 picometers. But when we talk about this order of magnitude, 2.5 million kilometers, 10 picometers is difficult to understand. So I try to find this example. Imagine we are here and we need to measure variations of distances with someone that is in Sydney, other side of the Earth, by less than a tiny part of a virus, actually 10,000 times of a virus. That's exactly what we want to achieve with LISA. Okay, so for the variations, I think that's a good example to understand the challenge behind this mission. But for the distance of 2.5 million kilometers, I found this example. So 2.5 million kilometers is more than 6 times the distance between us on the Earth to the Moon. So now the question is, how do we engineer this level of precision? And this is the talk I want to do today. So I want to present all the challenges that will make this possible. And I might sound a bit obsessed with the distances, sizes today, but I think it's important to understand all the engineering behind this mission. So the first question, and now leaving aside all the distances between the satellites, let's focus on the hardware, let's focus on the spacecraft, and if I would be next to a satellite, how big it will be. I don't know if you know, that's a question I made myself not long ago, so how big it is if we are next to it. I made this exercise, so the guy you see here, it's myself. So basically, one satellite, it's roughly my size, a bit less. Okay, I'm not tall, but this is the size. So the three of them together in the stack configuration, this is the launch configuration I will talk about later. It's roughly 3 times my size, so laying on the floor is also 3 times, so it's 3 times, 3 times, 3 times my size. And in terms of mass, and this is the dry mass, so no propellant, it's roughly 30 times my weight. Don't make the calculations, I'm fine with my weight, but it's roughly 30 times my weight. So the three of them is actually 19 times my weight, but this is dry, so in total is 8 tons with the propellant, what we will launch. There is a video here that we cannot see, and that's a pity. Okay. Anyway, here we had an exploded view of the satellite, so I'm going to show you what we have inside of the satellite. So let's focus on the inside of the satellite. Okay, here it is. I don't know why it doesn't work. Anyway, we go ahead. So what do we have inside? On the left side, we have the payload. On the right side, we have the platform. So we are going to see what is on both of these sides. But before entering into the details, I want to explain something that is pretty basic. You may all know what this is, but I think it's important, especially for LISA, to understand the difference between the payload and the platform. So if we take this analogy, it's a very simple one of a wheelbarrow. The wheelbarrow itself with the frame, the holders, the wheel, etc. That's the platform. What we put on top, what we transport with the wheelbarrow, that's exactly the payload. In this case, are the bricks, the product we deliver. So I always like to explain that the payload is the reason the spacecraft exists, and the platform is everything that makes the payload work. But I have bad news. On LISA, this differentiation is not so clear. It's more like a coffee machine, and I'm sorry, but I'm not an expert on coffee, but I think coffee machines, but I think this is a good example for LISA. It's more like a coffee machine, so of course we have the part that produces the coffee, the capsule, and so on. That's the payload, and all the rest is the platform. But of course, in a coffee machine, if we don't have the temperature enough in the water, if we don't have the pressure, the product we deliver will not be good. So the coffee we will get will not taste well. That's exactly what happens on LISA. We need to ensure that everything works perfectly together, everything is aligned, so the defects, the control, the attitude control of the satellite, magnetic-wise, EMC-wise is clean, etc., etc. So there are all the aspects, structurally, thermally, everything needs to be super well aligned to be sure we can achieve these 10 picometers of precision we need for LISA. Okay, let's focus now first on the platform, and here I have to say, sorry, I didn't present myself. I made it on purpose. So I'm Juanpa, part of the ESA team, working on the LISA, on the payload, on the LISA payload. So I'm the payload system engineer. So today I will go very quickly through the platform. That's the progress we made in the last year since we, roughly the last year since we selected the prime. My expertise is more on the payload, but anyway, I will try to present it the best that I can. I don't know why. So, okay, let's start from the outside of spacecraft. Very quickly, there are many elements here. The white ones we see, those are the lateral panels, those are radiators. We'll see them later on. The blue parts on the bottoms are the solar panels. We don't see them, they are behind. On top, we have the high-gain antenna. The two openings that we see on the sides, the big ones where I call them the MOSA 1 and MOSA 2, those are the moving optical subassembly openings. Remember this one, we will talk about the MOSAs quite a lot today, and many other elements. I don't have time to go through all of them. Then if we start opening the lateral panels, so this hexagonal shape, we start opening them, and there on these panels, these are radiators, and there we will mount both platform and payload units. Also, you see here already the nitrogen tanks. And if we keep exploding the satellites, then we see a bit more of the structure. So again, the panels, the white ones, and then there we see one of the key elements. This central tube is where the MOSAs will be mounted. So, okay, that was very quickly all about the platform. Now let's go to the payload side. And here we see this V shape with the yellow part. These are the baffles for the telescope. We have two. And then we have the structure that surrounds and that keeps all together. That's what we call the LCA structure. This is the LISA core assembly structure. On the right side, we see the LISA core assembly. That is basically these two MOSAs together. And then if we split them in two, they are symmetrical. We have the two MOSAs, the two moving optical subassembly. So let's, oh yeah, I forgot this. So why do we have this V-shape? This is pretty basic stuff, but we have a triangle, so we need to point to the distant satellites. We need to keep the laser link between them. That's why we have two. And then, as Nora already explained, these two parts, well, now the baseline is only one will move, but basically, as Nora already explained, this constellation need to breathe, so they need to move. They don't move very quickly. It's every 12 hours, more or less, that they will be moving. But this injects one of the challenges we have on LISA, that are the harnesses. So as you can imagine, inside of this LCA, the LISA core assembly, there are plenty of elements that need to be connected with harness. We don't have Wi-Fi in space. So we need to ensure that all these elements are connected and they are moving. And of course, we need to ensure that the harness don't break and, well, they don't inject extra torques, et cetera, et cetera. So this is one of the big challenges that we are working now on. So just to give you an idea, there are harnesses here of more than 7 meters length. So it's a quite complex routine, and yeah, that's one of the main challenges we are facing right now. Okay, again, yeah, I don't think it will work. Okay, no, we cannot see the video, but here we are exploding and separating the MOSA into 4 parts. The ones we see here in this slide. So the first one is the telescope, the one receiving and emitting the laser to the distant satellite. Then we have the OPA, the optical bench assembly, the MOSA superstructure, the MSS, that is the one keeping all together, and finally the gravitational reference sensor, the gravitational reference system. So let's focus now on the optical bench assembly. What do we see here? Here in green, surrounding the yellow part, we have the MSS that is holding this and also connecting the telescope and the gravitational reference system, and in yellow is the OPA, the optical bench assembly. And we have many elements here. You see them here. It's quite a number of elements. I don't have time today to go through all of them. Very, very quickly, let me explain that we have the side A and side B. This is not a big element. It's, well, only the optical bench is 45 centimeters. The whole setup together with the MSS ring, it's, I don't know exactly the size, but it's roughly 60 centimeters or something like that. And why do we have 2 sides? So if you remember, on LISA, we are interested in measuring the distance between the test masses in each satellite. And the way we do it is we measure the distance between the test mass and the satellite, the test mass and the other satellite, and then the distance between the spacecraft. So basically it's kind of 3 steps: the internal distances between the test masses and the spacecraft, and then the distance between them. So what we do on the side A is to measure the distance between the 2 spacecraft, and what we do in the side B, and this is the one pointing to the GRS that we will see later, is where we measure the local distance, so how the mass moved reference to the spacecraft. So far, I have been just showing sketches, nice stuff, but we're already working on hardware. So this is actually the second optical bench we produced. This is the STM. This is made of Ceradur as the telescope. It's thermally a very stable material. We see there a hole. This is because, well, we don't saw it before, but basically the laser needs to go from one face of from one side of the OVA to the other side, and that's the hole we will use to path the laser from one side to another. We have a little periscope there, and we allow the laser to go from one side to the other. Again, a bit more of hardware. This is the MSS ring, so this is the structure holding the OVA, the telescope, the GRS, and also some bracket for the harness are there, and this is also an STM that we have already built. Well, that's a video. Okay, we cannot see the videos. Anyway, what we see here, so if you remember, we have this V shape with the two telescopes, the baffles. I have this mounted one side to show you where the GRS is, the gravitational reference system is. So on the left side, we see a fully mounted MOSA. On the right side is dismounted, and we see the green is the MSS ring, the optical bench we just saw before, and then the last element there, this cylinder, this is the gravitational reference system, and the pipe we have on top, that's the bend duct that will allow to extract the remaining gases inside of this tube where the test mass is. So what are the functions of this system? It has many functions. This is somehow the heart of the mission. So it's the one in charge of holding the test mass during launch, of releasing it, grabbing and ungrabbing it during non-operational activities. It will be the one measuring the position of the test mass, giving the inertial reference to the spacecraft. So here, this is also something very particular of this mission. The spacecraft will always be following the test mass because we need to ensure that it's free-falling, that it's always floating. And it's also the optical reference because the laser path of this side B will enter into the inside of this cylinder and will hit the test mass. So that's the optical reference of the system. But I'm sure Rita will explain this much better and much more in details later on. And then inside, and this is a LISA Pathfinder picture, but I think it's very nice to see and to understand what we have inside. So this is the test mass. It's not a big thing. It's a 46 millimeters made of gold and platinum. And well, Nora already explained quite a bit on this, so I don't want to spend much time here. And yeah, as we, well, both Nora and myself were explaining before, this parts will allow to move, so each of them, it's 0.75 plus minus degrees. So the axis for the rotations of the MOSAs is exactly the gravitational reference system. And let's talk now about two main concepts. So the first one is the model philosophy, and then we will talk about how the mission will be tested. And this is quite important to understand why it takes so long to make a mission like LISA. So we need to go from the concept to a flight hardware, to a hardware that will fly. How do we do this? So in LISA, we start with the EBBs, so the breadboards and the electrical breadboard models. Then we go to the engineering models, and this is somehow part of the concept and risk reduction. Actually, the EMS is more part already of the engineering validation. So we were talking before about PDR, CDR, et cetera, et cetera. The PDR will go here with before the EMS, the engineering models, where we test the functional, electrical, interfaces, and so on. Then we will have the avionics model. This is to validate basically the interaction between the hardware and the software. We also have test bench specifically for the software test bench and the software validation facility. And then here we start with the qualification. And this is something specific of this mission. We don't have a qualification model as such. We will qualify first with an structural and thermal model. One spacecraft will be dissipating heat. And then to qualify the stack configuration, so the three of them, we will use two SM, that is only structural models. We put them together, we test we qualify the stack configuration, and then we enter into the next phase, that is the flight build. But of course, we cannot qualify all the hardware with STMs or SMs. We need the first flight model, what is called the proto-flight, to finalize the qualification. Then we produce two flight models, so the three of them, the proto-flight models and the two FMs, will form the constellation. And finally, we have the flight spare, so we have an extra spacecraft. In case there are issues, we have a replacement. And then let's talk about the test. And I will go very quickly. I will show you some videos. I don't know if you have ever had, well, videos I don't know if we will be able to see, but anyway. I don't know if you have ever had the chance to see how a satellite is tested, but here I summarize a bit the full process. So we need to ensure that first it survives the launch, it operates in space, it stays quiet, especially for LISA. We need to ensure it stays quiet so we don't inject any EMC noise. There are no magnetic forces inside moving the test mass. Remember, we need to measure 10 picometers, so whatever noise we inject inside of the spacecraft will affect this measurement. And then we need to ensure it produces the science we all know and we all want to produce. So basically, we do some mechanical test, vibration, acoustic test, and so on. We put the spacecraft in thermal vacuum. We do magnetic and EMC test to test that there is no noise, there is nothing affecting the test masses. We check that everything works together functionally, the commands, software, etc., and then finally we do some optical checks to verify that all this interferometry, etc., works in the satellite. So, okay, we will not be able to see this, but this is basically Plato. That's a mission I was working before LISA. And, well, we see here the spacecraft placed in a shaker. So in the video, you will have seen how the spacecraft moves up and down. So we always put the full spacecraft in one of these shakers. We can change the axis to test the different axes. And here we are simulating the structural loads that the spacecraft will suffer during launch. Here also a picture of a spacecraft inside of an acoustic facility. This is our acoustic facility at ESA. This, well, you see a bit the scale of the speakers. So with these speakers, basically we simulate the sound pressure it will suffer during launch as well. Of course, if we will enter inside of one of these facilities when it's testing the satellite, we will die. The loads are quite high. And then, well, we don't see it here, but the spacecraft is moved inside of a big cylinder, a big thermal and vacuum chamber. We pump out all the air, and we simulate the vacuum that we will have in space. So these are few of many tests that we need to run to verify that the mission will work in space, that the spacecraft will work in space. And finally, the launch. So the configuration for the LISA launch is a single launch architecture. Here, we will launch in an Ariane 64, the three of them together, as we saw before in the stack configuration. And basically, after more or less 35 minutes, they will start detaching one from each other. So, well, the first thing we do is we spin them to stabilize them, so to ensure that when they are released with some springs. We inject this momentum, this spin, so in case of any variation on the springs, they don't start spinning uncontrolled. So basically, they start spinning, and then every 500 meters, we separate them one by one, and it takes roughly 18 months to reach the final configuration, the operational configuration, so this triangle constellation we saw before. And let me finish this presentation with a reflection. So scientists study the world as it is. Engineers create the world that never has been. And yes, I am an engineer, but my purpose today is, and I hope when LISA start measuring gravitational waves, you will all remember that behind every scientific information we get from LISA, there is an amazing engineering behind of it.
Oh, there it is. Okay. Thank you, Juan. That was great. I agree. We can't do this without our engineering friends. Do we have a question? Yeah.
One very quick question about the testing. You say vibration and so on. Is there any planned performance test at the payload level? I mean, to test the level of performances. Are you thinking, because it's very hard, but maybe we can try to do something.
Yeah, of course. So this is part more on the last square we have here. So the payload and optical, all the performances somehow will be measured all over the life of the test. Of course, not all the performances will be able to measure here. I mean, we cannot simulate the 2.5 million kilometers here on Earth. But yeah, there will be many performances measuring not only at the end, but also in between. We also measure that all the performances are met. At payload and also spacecraft level, of course, yeah.
Other questions, Jeremy?
Excellent. This is a question from online. What tests, analyses are foreseen to make sure that LISA will be compliant with the particle radiation environment in space?
What test you mean? That will be performed? Well, this is part of the EMC and magnetic campaign.
And as long as I've got the mic, I had another question. Are all three spacecraft exactly identical, or is one going to perform any additional communications, that sort of thing?
As far as I know, they are all identical. Yeah.
This is Chris Hirschman from the Applied Physics Lab. I wondered if the testing plan was different for the flight units as compared to the proto-flight unit.
Yeah, because we need to ensure that, so the qualification models are always tested a bit more than the flight models. So these are the qualification levels, what we call qualification, levels. And for the flight model, we use acceptance levels. So they are a bit lower, and we don't stretch that much the spacecraft. So yes, it's different, especially here that we don't have a qualification model and we need to use the proto-flight model to qualify. So yeah, there will be one spacecraft that will suffer a bit more than the others.
Other questions? Okay. I will ask one last question then. So I am a scientist, not an engineer. So when I see things like the harness and, right, that kind of terrifies me. And so are there like, the complexity is enormous, especially as we get closer to LISA. So what do we worry about single point failures, and how do we test for that and guarantee against it as we kind of make the design more and more complex as we get closer to the end?
So single point of failure, that's something that we always take into account when we design. So it's part of the design itself, and of course it's tested. So it depends on at what level we go, but for instance, if we have a single point of failure in a cross-strapping, for instance, we test it before, so at unit level. For the harness that you were mentioning, the harness, we are doing some models and we are routing them before, so we are checking what the impact is of the bending on the harness, how does this affect the optical paths, and so on. So this is all tested, especially for the single point of failure. If they are detected, then they are tested even earlier than I expect. This is only a spacecraft level, but we go at unit level or even at breadboard level. That's the things we also test at the breadboard to ensure that the concept will work and we won't have any issue. Yeah.
Okay. Any last minute questions from Zoom? Are we good? Okay. Let's thank Juan again.
Yep. Thank you. I'll give you 5 minutes before the end morning.
Okay. Okay. Our last speaker for the morning plenary is Oliver Jennrich, who's going to talk to us about the LISA performance overview.
Okay. Thank you very much. Thank you for your patience while we are running through the inevitable problems with the AV. So my name is Oliver Jennrich. Together with Nora, I'm one of the European Space Agency project scientists on this mission. This will not be a science talk because I have been asked by our performance office to stand in for Martin Judson, who can't make it here, to give you an overview about the work of the LISA performance office. So in many ways, this is something where, sorry, no, that's fine. I think it's fine. Yeah, there you go. Where we are living in the interface between the project, where we had just had a nice talk from Juan, and the science for which most of you are here. So let me introduce you to the gang of criminals there. So yeah, the pictures are a little bit mugshotty. I apologize for that on their behalf. So Martin Judson in the top center there, Eric, Joffre, Michele Amano, and then Rafael and Pedro, our newest acquisitions in that team. And this is the core team. I tried to put as many logos I could remember around them. So if anybody is working in the performance area and does not see his logo there, that's my fault, because I did not check carefully if I actually have everybody in. But it's a relatively large number of people who work on the performance of LISA. So I also like to give you some idea about the where this performance team is located in terms of interfaces. There are a lot of talks and interfaces to the proper teams, the payload team, spacecraft team, the NASA ground segment, the DDPC, science operations on our side, mission operations, and the instrument payload teams, the instruments which at the end contribute a significant part of our performance. Now, what are we doing in everyday life? So there is this funny vicious circle where you start out, you can start at anywhere in that circle. Let's say you start at the upper right with the performance budget. You break that down to the related system budgets. You build performance models. You create related technical information. You run simulations for performances, and you're back at the performance budget because you might realize that what you thought is a good assessment or a good allocation for a budget is actually a really bad idea because you will never be able to make it. And then you start reiterating that until you have a reasonably stable and doable performance budget. Now, I'm kind of surprised that I'm maybe the first one who shows this slide today, but this the sensitivity, but there you are. So you all know that slide, I guess, about the sensitivity of LISA and a little bit of the core characteristics of LISA, which we have listed here on the right-hand side. We have continuous observation that distinguishes us from many of our other missions that we have, where we have pointed or scheduled observations, depending if you have a telescope or a survey. It's an all-sky observatory. This is certainly unique. None of our other missions is an all-sky observatory. Even some of them observe a large area of the sky. We are observing gravitational waves. That clearly is something that nobody else does at the moment in space. We are planning for 4 years of data collection, but if you will probably hear later from some other speakers that everybody pretty much expects the mission to last as long as it takes to run out our cold gas for compensating the non-gravitational forces. And we are doing time domain measurements. That's something that we have to remind ourselves occasionally. Certainly I have to remind myself occasionally, because all we are seeing here on those slides is typically a frequency-based picture. But keep in mind, intrinsically, this is very much a time-based measurement, which is then later converted. Now, that sounds all very abstract, and let me quickly remind you okay, so while this is building up, I'd rather have that way and then talk to you through. This is the disadvantage if you don't do all the slides yourself. You sometimes run into surprises. So what are we doing in practice? We are employing something that's called a time delay interferometry. Most of you will know what that is. Some of the very early pioneers are in the room. I saw Michele somewhere. So talk to him if you want to have a real detailed explanation. But what we need to measure is the fluctuations in the distance between test masses, effectively. And we need to make sure, and usually what I'm saying is that's the easy part. We know how to do interferometry, and we know how to do distance measurements. The really difficult part is to make that stick so that what you're measuring has something to do with gravitational waves and not with all the other nonsense that's going on the spacecraft. So we need to shield these test masses from all non-gravitational forces. And then we need to measure the relative distances because we don't measure test mass to test mass. We measure test mass to spacecraft, spacecraft to spacecraft, and test mass to test mass. And what we also need to do is, because we have a lot of frequency noise there, we need to kind of synthesize an experimental condition that our ground-based colleagues have built in. Ground-based telescopes, detectors work on the principle of having equal arms, so most of the frequency noise is gone, or doesn't show up at least. For us, that's different. We can't have equal arms, not without any undue efforts, so we need to synthesize this. This is where the time delay interferometry comes into place, where we combine measurements from different spacecraft, delay them, add them together to build a synthetic white light interferometer, if you want. And if you then take into account that we're not only having different arm lengths, but changing arm lengths, then things become slightly more complicated, but still doable. And we need to combine all those measurements to make sure that we have the right performance at the end. So I told you that I will present something about the current work of the Performance Office, but I've never really told you what we mean with performance. And there are different things that go into there. The first and quite obvious thing is the strain sensitivity. This is what I showed you before. It's effectively a proxy to answer the question, how well can we resolve gravitational wave signals? How well can we address the questions about the parameters of the sources and derive astrophysical questions and answers to that one? Another very important question is availability. We say we measure all the time, all the sky. How true is that? Can we actually make sure that the instrument performs 24/7? Then there's another question. If you want to relate your sources and your measurements to something that is of astrophysical origin and importance, you have better some clue about the timing of things. So how well can you determine the question, when does it happen? So you need to make sure that the timing of your instrument is good enough so that we also can correlate with other observations. Question is about the response of the instrument. How do you know that when you measure in the instrument a certain signal amplitude, how does that relate to a gravitational wave amplitude? Ground-based machines solve that problem by a dedicated calibration. You push the mirrors around with a known force, and there you go. That's complicated enough, but For us, it's mostly knowledge of the arm length, knowledge of the laser wavelength, knowledge of the position of the spacecraft. So where are we in the sky? How is the antenna pattern looking? And how does our delta L that we measure at the end relate to an age of our gravitational waves? And then a very important question: how well do we know our instrument? How well do we know the noise of our instrument? Some of you are very interested in stochastic sources, and stochastic sources in many aspects resemble a little bit like unknown instrument noise. So to have those sources under control, to have a fair chance to write a paper later on and saying we observed some gravitational wave background, we need to have the performance of the instrument, the noise, and all that under very good control. So this is quite a task, and this is also the reason why this is the first mission in ESA history that goes to the length of appointing a full team responsible for performance. We have missions where we have performance engineers, sometimes a full one, sometimes just half of them, but this is really the first mission where it has also sunk into management that we really need to invest in having the right amount of people and the right kind of people working on performance. So I'd give you a quick overview how that works in a formal process. We are now dipping our toes a little bit into the engineering world, which you have seen is much more process-oriented than the science part. And so we are starting out from the science requirement document. That is effectively your document. I mean, the project science part of the mission compiled that with the help of the people in the science team. And then we derive from those high-level requirements. For example, we want to be able to see supermassive black hole coalescences. We compile that down and break that down to what is called the mission requirement document, where this is much more about we need to measure changes in distances of such and such, or we have to have thermal conditions on that spacecraft of so-and-so. And it flows further down to the requirements on the instruments. If you're working on the phase meter, you better make sure that you can resolve a certain phase change in the incoming laser. So let me start give you an example. And I picked free fall of test masses here, not because it's our biggest problem, but because it gives you a nice illustration of how detailed things can become. So one of the things that the colleagues who are responsible for the test mass and the GRS will tell you is the molecular impact on the test mass, which means that we need to control the vacuum, and that one of the solutions there is that we pump out into space early on. Another problem there is the low level of actuation noise. What are the solutions? What are the concepts we want to have there? We want to maximize the stability of the actuator voltages, or minimize the noise, in other words. We want to minimize the required levels of authority, because the more force you have to exert, the bigger the noise impact is. So that means that we have to have a good gravitational balance to reduce the DC forces. We need to take care of dynamical couplings, control of force gradients with gravitational gradients, electrostatic gradients. We want to minimize the jitter between the test mass and the rest of the mass, so the spacecraft, which means that we should not jiggle the spacecraft around too much. Now, you heard from Juan that the spacecraft is quite heavy, so it takes a little bit to jiggle it around, which works in our favor, obviously. and impact of charged test masses. We have all seen that in LISA Pathfinder. What happens if the test mass is charged? It couples to electrostatic forces. So you have a noise on the electrostatic force. Your test mass jiggles around. So that leads us to ask for a discharge system, of which you will probably hear later during this conference quite a bit. And we put all that together, and we can come up with a budget for the free fall of the test mass. What's our performance budget? It's an allocation. That's up there. That's, neither here nor there. So if you're interested in those things, but it's 2.7 femtometers per second squared per root hertz, adorned with some frequency shape factor that really isn't terribly important here, but tells you a little bit about the system architecture there. And then you have a lot of effects, and here's just a sort of collection of them. Actuation, magnetic, laser radiation pressure, because we measure the test mass with the laser interferometry, Brownian noise, stray electronics, and so on and so on and so on. We break them out into much smaller details and hand them over to the prime and the custom furnished instrument providers. So, and the color coding here is effectively which of the requirements goes to whom. So the light green ones, for those who can distinguish that color, are the ones that we are asking the CFI providers, so the people who built the GRS. The dark ones are things that are more on the spacecraft side. So these are interfaces and interface requirements that this spacecraft builder, the prime contractor, has to establish and guarantee. Indeed, so requirements on the GRS and the prime, as I just told you. Now, you do all that and you end up with plots like that. Let's focus on the big thing on the left-hand side first. This is a breakdown of a large number of noise sources, already sanitized a little bit so that you can actually see something and that the key actually fits on the slide here. But they are all added up to the top line there in black. And so what you can see, this is an allocation. We say, we are starting from here. I give you the allowance for this amount of noise, and I give you the allowance for another amount of noise. And then reality is what we call the mission best estimate at the moment. And these are the estimated performance of the subsystems, assuming the worst possible parameters, right? So, and what then happens, you ask your computer to fill in the difference between the squared sum of all those sources and your requirements in green if you're under and in red if you're over. So you see this tiny little bit of red there at 10 to the minus 5. Fortunately, we are not concerned because our remit ends at 10 to the minus 4 hertz. And at the low frequency, at the high frequency range, we see we are not critical at all. So all of our performances are green. You can also ask yourself, so what is the real problem here? Well, you see that where are our drivers? You can identify residual gas around the test mass charge control, the dynamical couplings and magnetic forces at different frequencies, and then you can make sure that those are most critically looked at. Now that was just the freefall budget. We have a lot of other things, but for the sake of simplicity, I say we add the GRS, that's the center part, the optical metrology system here on the left, and the post-processing on the right. We add them all together and we look, are we compliant? And then you get plots like that. It's a little bit confusing. So this is the ratio between what you think you can achieve and what you should achieve. So everything which is above 0 there is good. Everything that's below 0 is bad. And the blue line there, which is labeled as MBE to SIRD, that is what we absolutely want to keep, because that's our margin between the mission requirement, what the engineers are willing to build, to the science requirement, what you guys expect us to do. And we want to have a little bit of a safety margin there. And so what you can see there is that if you look at the difference between the best estimates, MBE to MRD, that's the green line, you see that we have about, at a minimum, 30% margin, right? And the mission requirement has a margin against the science requirement of always 10%. And so the problem is that this all looks very nice and shiny, but the modeling that we are actually doing does not have any margin anymore at around 1 millihertz against the mission requirement document, right? Why is that important? Because that tells you that you have very, very little things to play around with at this particular frequency. And it is where at the moment a lot of effort goes in to make that maroon or orange curve move up a tiny little bit. I circle that in red because it kind of looks bad, but you know, there's also the green part. So we have the, against the science requirement is still fine. But if I look at the strain plot where we say which is our sensitivity that we really want to reach, and I push this red circle up into that plot, and you see, well, that's not really difficult, or that's not really dramatic, right? We see the black curve, which is where we are supposed to be, and the orange curve, which is the current best estimate under worst conditions, and we still have a little bit of margin there. That is the 10% that we always have between what we attempt to build and what you want to have. So it is, the red circle is a homemade problem, so to speak, based on the insistence of having a certain performance margin. Now, with all that, I spoke about modeling. We have a couple of system models that get into consideration here. We have models for the TDI transfer function, so how is the signal treated by this idea of delaying and linearly combining measurements? And there we have very well developed simulators. We have the usual engineering bag of tools for the optical metrology system, the structural thermal analysis, performance analysis, finite element analysis, OMS system models, so that we can predict the performance, a parameterized prediction of the performance. We have an optical power model, how many photons are actually coming onto the photodiodes with which we then eventually measure the beat node between local lasers and received lasers. Where does the power go? Where do we lose power? Where do we have to watch out to make sure that the components actually hold the requirements? Now let me come to the performance model. There will be a test later. So it's a custom Python performing modeling infrastructure, a lot of them done by Martin Jötsen, who apparently needs no sleep. We have more than 900 nodes. That's a moving target, right? So I don't know where the number actually is, but it's large. Each node represents a model or a parameter, so you can hook things in and expand a node to a model or compress a model to a node. We have all the metadata with the documentation and all that, links to requirements and budgets, so that should you ever want to figure out why on earth this thing is what it is, you can look it up. The nice thing is it can produce endless performance plots, so effectively all of the plots you've seen today on my talk are produced by that model. you very quickly run into the question how to distinguish 120 different traces on a single plot. The answer is you don't. You can identify performance drivers, which is your worst enemy at any given point in frequency and time. And also very nice, performance drivers here just for the example for the test mass, where we see things like the actuation stability, the magnetic noise, and the Brownian noise, and it's linked to the various different performances and requirements so that you actually know where things are coming from. Very important for a project of this size, you need to be able to create documentation because you cannot rely on the fact that you can actually speak to the person who once dreamt that up, because those people might not be around, they might be retired, or they might have forgotten why that number came together in the first place. It's a common problem. So we have, thank you, we have have a way of doing performance document production where you can go as deep as you want. Last important thing I want to tell you is we have most of the things are Monte Carlo-able, if that is a word. So we write here at any level, that's probably wrong, but on most levels, we can run Monte Carlo schemes to identify useful intervals for our performance analysis. No point in asking for something that is either meaningless or unachievable. Just a little bit about the milestones. You're here. We just had in February, NASA had its KDP-B. We will have our mission PDR starting end of the year. So we are right there. I only used that slide to go to the next one, to expand a little bit what we have done and what needs to be done. So we have all the budgets and measurements traced. We have agreed on the performance requirements, which is a difficult part. We implemented a performance model, all that, but there's also a lot of things to do. We need to come up with an in-orbit verification plan. There was a question before, how do we verify things? Post-processing, model review, we need to do, we need a couple of operational analysis done, a verification plan in general, and a traceability analysis. If you build an instrument and you ask yourself, why do they push me so hard for that freaking number? We need to be able to tell you why. I think that's not only politeness, but good engineering practice. So some advertisements towards the end of my talk. I have effectively my last content slide here. So there will be more just now, just in a couple of minutes. Rita will tell you about the GRS. We will have the optical metrology system overview by Ryan. On Tuesday morning, we will have interferometer testing by Ada on Wednesday morning. LISA GRS sensing and actuation electronics, and with Heritage of Pathfinder, Luigi on Thursday. We have at least 3 parallel sessions on instrumentation. So if you're interested, go there, you will learn a lot. We have 2 poster sections, which deal exclusively with LISA technology. Let me finish with that slide. So if you have any questions, I'm happy to answer them. And one of my favorite cartoonists came out on last Friday with this nice idea. And with that, whee! Oh, and one last thing, because, I mean, Nora already mentioned that, but I cannot and will not end. I mean, if I could just go one slide further. Okay, so for the young ones among you, if you're interested working with us, talk to Nora or myself. Good.
Okay, thank you, Oliver. Any questions? I see Neil's hand over there on the far side.
Yeah, so Oliver, I think we have an astrophysical solution for your margin at 1 millihertz and it's like totally buried by the galactic binaries. But more seriously, like, isn't that sort of take into account that we should maybe, you know, a little bit more relaxed in that region?
I will come to you in the science team. If this ever becomes a real issue, we will talk to you and say, look, we can't hold that requirement, what do you think about it? Until then, I prefer to build the instrument or ask the engineers to build the instrument that we want to have. So, but yes, I know, I mean, it's not critical. We are aware of that. So we are not losing sleep about it at the moment.
I like Neil's confidence that he thinks we know what the galaxy looks like there. Other questions?
This is recorded, right?
Yes.
Okay, good.
Any questions from our webinar? Oh, sorry. Yes.
Hi. Can you go please to slide 13 or 14 where you have the forest performance budget? I have a question on specific entry about the spacecraft MOSA entry. Yeah, you know, I don't know the color, the curve with the mountains. I think it's purple. Not the right side. The one on the right side, where you have the best estimate.
Yes.
That one, it accounts for the simulation of the orbit, and also another question, it does have also the MOSA, only one MOSA working, or do you know if that is updated?
The new MOSA actuation scheme, to start with that one, is designed to not change any of that. We are still holding the requirements. I mean, that's a key thing. If you change operational architecture, you make sure that you hit the requirements, right? Otherwise, we need to talk about that. And this will, in the plan, hold the requirements. The other question, does this include the actual orbits? These things usually are based on the nominal orbit, which is one particular set of orbits that we got out of our mission operation system, our flight dynamics people. The real orbit will be the real orbit, so there might be slight changes, but also most of the things that the orbit does has operational consequences and very little on this performance, because the arm length, the change of arm length is tiny, and you won't be able to see that. It will be buried under the line thickness there.
Thanks.
Other questions? So I have one last one, Oliver. So as always, LISA is doing things that have never been done before, and I was very struck by your statement that we've never had a performance team before. What I'm wondering is, as we learn how to do things that we can't do like we do on the ground, like calibrating the instrument, are there lots of different things we're trying, or how are we going to decide what the best practices are, so when we build what comes after LISA, we know what to do?
It's not the first mission where we cannot check the performance on ground or aspects of the performance on ground. This is quite a routine thing. There are a lot of things that you effectively only can assess when you're on orbit. So the typical recipe there is you verify by analysis and tie your analysis or the models that feed into that analysis as much as possible into ground truth. So you test the things that you can test and then extrapolate to the things that you cannot test. So, I mean, Bill will tell you about the enormous amount of effort they do for the GRS system to make sure that the stray forces on the test mass are under control, despite the fact that we know that we can't test it on ground, right? But all the modeling is tied to some real measurements that give you an idea. That is pretty much in every single space mission I'm aware of, that happens. And if it's only stupid things like gravity release of the telescope, you build and test telescopes on the ground where they are under 1G. The moment you bring them up into orbit, the telescope goes, right? And changes the shape a little bit. But you have that under control because you can measure and model the shape. You have the shape change, you know the parameters, the elastic parameters of your material, and then you get it usually right. And then you assess the performance in orbit, and usually you're surprised that's a little bit better than you wanted it to be. Not always, though. And yeah, that's not unusual. What's unusual for LISA is that everything is tied together in the performance. Normally, people do not care about the instrument, when they are looking to the instrument performance, what the other instrument is doing at the same time. Or, you know, if something heats up on the spacecraft. That's really not the problem, usually.
Okay. If there are no questions from the webinar, we good? Okay. Well, let's thank Oliver and all our speakers again. Peter, do we have any announcements? Yeah.